Image processing includes a broad range of operations that go well beyond just changing the appearance of images. To give a brief tour through some of the possibilities, here is a sample image, which, like all of the images considered here, is a digital image that is stored in the computer as an array of dots called pixels. Zooming in on a piece of this image shows individual pixels as colored squares. The color of each pixel is represented inside the computer by a set of numbers called the pixel value. Selecting the image displays a row of buttons below the image, and clicking the Coordinates tool button brings up an interactive tool for examining individual pixel values. This image is an RGB image, which means that each pixel value is a set of 3 numbers giving the amounts of red, green, and blue light needed to get the color of that pixel. It isn't often necessary to inspect or change individual pixel values directly, but digital image processing does ultimately work by inspecting or changing or selecting or otherwise transforming those pixel values. Returning to the full image, the image dimensions function shows that this image is an array of pixels that is 1920 pixels wide and 1271 pixels high. One simple operation is cropping to select a part of the image, which works by selecting a corresponding part of the underlying array of pixel values. Sometimes it's convenient to do this interactively. For example, selecting the image and choosing Selection tool from that row of buttons below the image enables selection of part of the image by clicking and dragging. The selected part of the image can then be copied and pasted using ordinary copy and paste commands. Cropping can also be done programmatically using various functions like image crop or image take or image pad. For example, this shows the image crop function cropping evenly on all sides of the image to get a result that is 400 pixels wide and 300 pixels high. And this shows additional arguments included to specify cropping from the right and from the bottom of the image, which gives a result from the upper left corner of the original image. There are lots of things that can be done to change the appearance of the image. For example, this shows image effect applied to this image with sepia as the second argument, which gives a new image with a slight reddish-brown coloration. The sepia effect is achieved by changing the lists of numbers that give the color of each pixel. A similar result can be achieved using image apply, which applies a function separately to each pixel in the image. In this input, mean gives the brightness of each pixel, and coloration is introduced by adding in 3 numbers based on the amounts of red, green, and blue in the desired sepia color. Image operations like these that operate separately on each pixel value are sometimes called pixel-wise operations. Another common pixel-wise operation is color negate, which gives a type of color negative. Color negate is equivalent for this image to subtracting each pixel value from 1, which makes dark pixels light and light pixels dark, and so on. Many image operations are neighborhood operations that involve considering neighborhoods of nearby pixels rather than separately transforming individual pixels. For example, this input shows an image effect called edge stylization, which adds lines to emphasize the edges in the image. Edge detection can be done separately using the edge detect function. This input shows one of many ways of adding those edges as black lines in the image. In that input, the max filter function makes the detected edges thicker, color negate makes the edges black rather than white, and image multiply multiplies those black edges pixel by pixel into the original image. Edge detection and max filter are among the many operations that work by considering neighborhoods of pixels. There are also operations that consider the whole image or that sometimes essentially construct an entirely different image. For example, starting with a pair of images, the image restyle function can be used with those 2 images as arguments to get a new version of the first image in the style of the second image. The result is more than just a change in color or the addition of a few details. The result includes features and colors that are not present at all, except perhaps in some stylistic way in the original image. The image restyle function uses machine learning to make sometimes rather dramatic changes in the appearance of an image based on the style of another image. So far, the examples have been mostly about changing the appearance of an image, but there are many important applications in image processing, such as analyzing the objects in an image, where adjusting the appearance of the image is not the main objective. As a simple example, consider writing a program to count the objects in an image like this one. A useful first step in this application is separating the objects from the background and from each other. Removing the background is relatively easy in this example, and there are several ways to do it, perhaps the simplest of which is to just use the built-in remove background function. The remove background function returns a result in which the background is represented by including an extra number called an alpha channel in each pixel value to specify whether that pixel is part of the foreground or part of the background. The alpha channel function separates the alpha channel from the rest of the image and returns a result as another image. The display of that image shows the objects to be counted in white and the background in black. Separating an image into pieces like this is called segmentation, and the pieces are often referred to as segments or as components. The number of objects in the image can now be determined by counting the number of components, which can be done using the component measurements function. The component measurements function can calculate lots of different properties of components. Here, the component measurements function is used with count as the second argument, which gives a list with the number of pixels in each component. The result in this example shows three large components with large numbers of pixels, which are the components to be counted, but the result also includes lots of smaller components that arise from fine details in the original image. Zooming in on part of the image shows some of those smaller components. Those fine details could in principle be mistakenly counted as additional objects, and more generally in image analysis it is quite common that only components on a particular scale are of interest. A simple tool for removing the small components in this example is a function called closing, which has the effect of closing up the gaps between large components and nearby smaller components. The result now includes only the three large components. Closing in this example is equivalent to a combination of max filter followed by min filter. Max filter is a simple function that replaces each pixel value with the maximum pixel value of nearby pixels, and min filter replaces each pixel value with the minimum pixel value of nearby pixels. The second argument in max filter or min filter and in the closing function gives the size of the neighborhood to consider around each pixel. These functions also provide a simple way of reducing noise or fixing other defects in an image. For example, here's an image with some defects as black marks, and this shows the max filter function used to eliminate those defects. Max filter removes the black marks in this example because black is always the smallest pixel value, so replacing small pixel values with larger pixel values removes all of the defects. This operation also, however, makes the image lighter and enlarges light regions in the image which may be undesirable, and some restoration of the original image can be achieved by following max filter with min filter or by using the closing function. A more sophisticated way of fixing many defects in images is a method called inpainting, which uses methods based on machine learning to fill in selected parts of an image based on an analysis of colors and textures in other parts of the image. For example, this shows the inpaint function using inpainting to repair the defects in this example. The second argument in the inpaint function is an image called a mask, which specifies the parts of the image that are to be repaired. There are many ways of constructing a suitable mask. Often the mask can be constructed interactively, or in this example, since the areas to be repaired are black, those areas can be selected from the image using binarize to pick out only the black parts of the image, and then apply max filter to slightly enlarge those areas so that enough of the image will be repaired to get the desired effect. The result is the mask that was used in this example. For one last example, consider the task of removing the perspective distortion in this image, which will require a geometric transformation of the image. One general approach starts by identifying coordinates for a set of points in the original image and coordinates for the desired positions of those points in the transformed image. In this example, it's convenient to choose coordinates at the corners of a rectangle in the image and the desired positions of those corners in the result. This shows the highlight image function used to help visualize these two sets of coordinates. The coordinates in the original image are shown as red dots, and the desired positions of those coordinates are shown as white dots. Having identified corresponding points in the original image and in the desired result, the geometric transformation needed to get from one to the other can be constructed using the find geometric transform function, and that transformation can be applied to the original image using the image perspective transformation function. This example illustrates just a few of the operations that are available for finding key points in images and corresponding points in pairs of images and aligning images with other images and so on. Image processing more generally includes a broad and diverse range of applications, and there is a similarly broad range of things that can be done with images. An introduction to that range of functions can be found in the Wolfram documentation in this tutorial on image processing, and links to individual functions can be found on this guide page on image processing and analysis.